Hello students. Exponential functions. For each function, complete the table, graph the function, and give the domain and range. First function is f of x equals 2 raised to the x. When x is negative 3, we have that the y coordinate would be 2 to the minus 3. And that simply means to do the reciprocal of the base. The base is 2, so the reciprocal of the base is 1/2, and raise that to the positive third power. And a half times a half times a half will be 1/8. So when I do 2 to the minus 2, that's the same thing as doing 1/2 raised to the positive 2, which gives me 1/4. 2 to the minus 1 just gives me 1/2 to the 1, which is just going to be 1/2. 2 raised to the 0, any non-zero base raised to the 0 exponent will be 1. 2 raised to the 1 will just be equal to 2. 2 raised to the 2 power will give us a 4. 2 raised to the third power will give us a total of 8. And now let's review what happens when we have fractional powers. For example, 2 raised to the 1/2. That's the same thing as radical square root of 2, which is about 1.4 when you reach for a calculator. 2 raised to the 3/2. This means to do the square root of 2, but then cube the result. So it's radical 2 times radical 2 times radical 2, which can be written as 2 radical 2's, which is about 2.8. Negative fraction powers. So if you have 2 raised to the negative 1/2, we do the reciprocal of the base and raise that to the positive half power. And that just means we're doing the square root of the base. And I can square root the top and bottom separately, so we could do square root of 1 over square root of 2, which just gives us 1 over radical 2, which I could also rationalize and multiply the top and bottom by rad 2. So I get rad 2 over 2, and since rad 2 is about 1.4, dividing that in half, we get about 0.7. And if you had 2 raised to the negative 3/2, this would be 1/2 raised to the 3/2. So I could raise the 1 to the 3/2 and the 2 to the 3/2 separately, and I would just get 1 up top, because 1 raised to any power will stay 1. But we have 2 raised to the 3/2 we need to do still, and we've done that already up above. That was 2 rad 2, which if you rationalize this, you'll get rad 2 over 4. So that tells us that's about 0.35, we'll say. Now let's plot some points. When x was negative 3, the y coordinate was 1/8. So there's the half mark, there's a quarter mark, so 1/8 is about right there. When x was negative 2, the output was 1/4. When x was negative 1, the output was 1/2. When x was 0, the output was 1. When x was 1, the output was 2. When x is 2, the output was 4. And when x is 3, the output was 8. Now the other points, the bottom 4 points in our table, when x is 1/2, we had about 1.4, so somewhere in this area. When x was 3/2, we had about 2.8. 3/2 is 1.5, and 2.8 is up in this area. Negative 1/2 gave us about 0.7, so somewhere up in this area. And negative 3/2 gave us 0.35, somewhere in there. Our graph is going to be an increasing function. You might wonder what's happening with the graph as we go further left in the graph. If you were to pick x coordinates such as -4, -5, -6, etc., what kind of y coordinates would you get? So if we were to put one more data entry in here, let's pick -5, for example. 2 raised to the -5 would be the output. That's going to be 1/2 raised to the 5th, which is 1 over 2 raised to the 5th, which is 1/32. So we still get a positive number, but it's extremely small. In fact, you might have noticed a pattern here. Every time that the x-coordinate increases by 1, notice what the y-coordinate does. So x increased by 1. So from -3 to -2, we added 1. Keep that pattern up. Just keep adding the same amount. Notice what the y-coordinates are doing. To go from 1/8 to 1/4, we actually multiplied by 2. We doubled. To go from 1/4 to 1/2, again, we doubled. To go from 1/2 to 1, we doubled. This is sometimes called the doubling function, because every time x increases by 1, the y-coordinate doubles. Now let's take a look at this next function, g of x equals 1/3 raised to the x. When x is a negative whole number, so we have a 1/3 raised to the -3. But when you have a base to a negative power, you can do the reciprocal of the base, and the reciprocal of 1/3 is 3, and switch that to the positive power. So we just get 3 cubed, which is 27. When I have 1/3 raised to the -2, this is going to be the same thing as 3 raised to the positive 2, which will give me 9. And we do 1/3 raised to the -1 will just give me 3 raised to the positive 1, which is just 3. And then we have a non-zero base of a third raised to the 0 power. That's always going to give you 1. And we have 1/3 raised to the 1 power. That's going to give me just a 1/3. Whenever you have a base raised to the 1, you just get the base back. 1/3, and we're going to square this. This will give me 1/9. 1/3 and cube that base will give me 1/27. And let's see what some of these other fractional powers wind up looking like. So if you have 1/3 raised to the 1/2, that just means you do the square root of a third, which is the square root of 1 over square root of 3. And if you rationalize this denominator, it'd be radical 3 over 3. I'm not going to worry about decimalizing this, but you could do that if you'd like. If I do 1/3 raised to the 3/2, that means I'm going to do the square root of 1/3 and then cube that. So it's effectively going to be 1 over the cube of the square root of 3. That's going to be 1 over 3 radical 3. When you have 1/3 to the negative 1/2 power, so first make that a positive half power by doing the reciprocal of the base, and 3 to the 1/2 is just rad 3. Well, that's about 1.7. Now let's do the last one. If you have 1/3 as the base and you're raising it to the negative 3/2, this means you're going to do just 3 raised to the 3/2, which is the square root of 3, then you cube that, which is 3 rad 3. And since rad 3 is about 1.7, this is about 5.1. Okay, plot some of this data now on this graph. When x was negative 3, we had 27. I don't have room on this particular scale to graph this point here, so we'll just leave that off. Negative 2, 9, so there's a point right there. Negative 1, 3, 0, 1, 1, 1/3, 2, 1/9, 3, 1/27th. And you see that we're getting very close to 0, but we're not going to actually ever get to 0. Even if I do x as a very large number, like 100, g of 100 will be very small, but still positive. Trend you might notice that's happening here. So again, focus on the consistent fact that the x's, at least initially, are increasing by 1, right, as I go from row to row. Notice what's happening to the y-coordinates. To go from 27 to 9, you divide by 3, or you can think multiply by a third. And to go from 9 to 3, same thing, multiply by a third. 3 to 1, multiply by a third. So there's a clear pattern here. Every time x increases by 1, the y-coordinate is 1/3 what it used to be. A decreasing curve that flattens out and it's going to follow the x-axis like an asymptote. In fact, both of these graphs are going to have the x-axis as an asymptote, and the graph on the left, the asymptotic behavior is over here on the left side, and on the graph on the right, the asymptotic behavior is on the right side. Okay, now we're going to use technology to graph several examples of y equals b to the x for various choices of a positive base. Then we're going to complete the following statements. So I'm going to go to Desmos. I already have typed in y equals b to the x, and I'm going to add a slider for b. I'm going to change b so that's only positive. So let's say that it'll vary between 0 and, let's just go to 10. And let's do step size of 0.1. Okay, so this gives me a slider where I can control b, and you can see how as b takes on different values, we get different looking curves. When b is 1, y equals 1 to the x is just y equals 1. It's a horizontal line. I wouldn't call this one an exponential function, so we don't want the base to be 1. But if the base is more than 1, you see we get a growing exponential, and more steep the larger the base gets. But look what happens when b is between 0 and 1, and we get this, we're going to call a decaying exponential function. Now, in all cases, when you have a decaying exponential function like we see right now, versus a growing exponential function like we see right now, in both cases, notice what the domain and range is. All these graphs go left and right forever, so the domain will be all real numbers, but in all of them, the only possible y-coordinates are positive. Right? We don't have any negative y-coordinates here. And they all have a horizontal asymptote at y equals 0. Sometimes the asymptote's to the left, sometimes it's to the right. Complete the following statements. If b is more than 1, the function is, let's use the word increasing here. So we have an increasing function when the base is more than 1. In the case of a growing or an increasing function, we're going to call b the growth factor. For example, in the previous page, when the base was 2, we had a growing or an increasing exponential curve, and the y-coordinates doubled every time the x-coordinates increased by 1. Over here, you could say the growth factor is a third, but growth feels wrong because here the y-coordinates are shrinking. So we're going to call this a decay factor instead of a growth factor. And that's going to happen whenever the base is between 0 and 1, and the function will be decreasing, and we're going to call b the decay factor. In either case, the domain is all real numbers, so you can put a bold R here, or you can say negative infinity to infinity. And the range is, the only possible outputs were above 0. So in interval notation, 0 to infinity, not including 0. All these graphs that you see here for various choices of the base, none of them will actually intersect the x-axis. Now, one special base is the irrational number e, known as Euler's constant. And e is 2.71828182846. It's an irrational number, meaning that in decimal form, the decimals go forever and without a pattern. Another example, of course, is pi, 3.14, etc. Pi is an irrational number whose decimals go forever without a repeating pattern. E is an important number, as we'll see as we continue to move forward, but now we're just going to introduce it sort of out of context. But 2.7 we'll say roughly is e. So when you are trying to graph y equals e to the x, now first of all, e is a number, it's 2.7, so it's more than 1, so this will produce a growing exponential. And in our table of points, we really can't do much with this without a calculator, but if you have e to the minus 1, then you could just write that as 1 over e. When the exponent is 0, e to the 0 will just be 1 still. When you have e raised to the 1, that's just going to give you e, which we'll say is about 2.7. And e squared, we'll turn that into a decimal 2 in just a moment. In Desmos, e is a protected letter. If you type in 1 divided by e, it's going to assume that you're referring to Euler's constant. And so 1 over e is about 0.37. E squared is about 7.39. And plotting these points here, negative 1 comma 1 over e is about 0.37, so it's, in this area here, 0, 1, 1e, 2.7's up here, so there's 1e. And I don't have enough room to plot this last point, but that's okay. We do expect to see a growing exponential curve. So another thing to notice when we graph exponential curves, they all have the same y-intercept. They all go through 0, 1. The only way we can change that is by doing vertical stretches and or vertical shifting, but your basic exponential parent graph b raised to the x will go through 0, 1. Okay, so speaking of transformations, use transformations to graph the following function. Give its domain and range. Let's start with a parent function of just recognizing that 2 is our base raised to the x. And one thing I want to mention about this minus sign real fast. We said that when you have b to the x, we only want to consider positive bases, but we don't want a base to be 1. Let me show you why we don't want a negative base. Because if you have a negative base and then you try to plug in a 1/2 power on this means that you're trying to do the square root of negative 2, which gives you imaginary numbers. It's not real. And this actually happens for lots of different choices of an exponent when you have a negative base. A quarter is going to be a problem. 3/4 is going to be a problem. The trouble exponents are everywhere. So we avoid this by just saying don't let the base be negative. So you might wonder, when you see this expression, some people look at this and say, oh, I see a negative base. You have to be careful here. When you see this, you have to interpret this as negative of 2 to the x. So just be careful about that. And I say, hey, what's the base? Don't say negative 2. The base I see here is positive 2, but then the 2 to the x is being multiplied by the negative 1. And 2 to the x goes through 0, 1, and 1, 2. Those are two easy points to find on it. And it's a growing exponential, so it looks something like this. It also goes through 2, 4, so I might as well put that point there. So here's our parent. Now we're going to do the transformations. If you multiply the rule by negative 1, it'll reflect across the x-axis. This is a graph of negative 2 to the x. The next thing I'm going to do is the shiftings. To go from green to orange, you replace the x with x plus 1. If you recall, that means that we're going to do a shift left 1 unit. So the 3 green points I put on here, I can move them all left 1 unit. And then the final step, we're going to take the previous step and add 4 to all of it. And when you add 4 to a function, you shift up 4. When you shift the orange graph up 4 and make the blue graph, the horizontal asymptote is going to go with it. This is going to be a horizontal asymptote. Now I'm going to go ahead and draw. And so there's my answer. This is the m of x graph that we were after. And then let's do domain and range of this blue graph. The domain will still be all real numbers because the blue graph goes left and right forever. Your exponents can be any number. They can be positive, negative, fraction, 0. It really doesn't matter what x is. It can be any kind of number. But the range is certainly limited here. And the blue graph goes as far down as negative infinity. So if I think low to high, and then it goes as high up as 4, but not getting to 4. So the range will be negative infinity up to 4, but excluding 4. In other words, y has to be less than 4. Okay, let's do the next one. Another transformation, this time this parent function is e to the x. The two easiest points would be 0, 1 to find and 1e. And 1e is about right there. Remember, e is about 2.7. And we have a growing exponential. And our first transformation is going to be what happens when you replace x with negative x. We reflect across the y-axis. Y-intercept is still going to be at the same location right there. When all the points reflect, we're going to wind up with a shape that looks like this. So that's one way to create a decaying exponential out of a growing exponential, is to do a reflection across the y-axis. Now let's do the next change. Let's do the vertical stretch. So multiply by 3, and this is going to be a vertical stretch by a factor of 3. So all the points will be 3 times as high as they used to be. So the y-intercept, instead of being at 0, 1, will be at 0, 3, and we're just going to get a vertically stretched version. All the points on the green are 3 times as high as the points on the orange. And if the orange is approaching the x-axis over here off the right, then the green will eventually approach the x-axis as well. So we still have the x-axis as an asymptote, even though I did a vertical stretch. Now, the very final transformation is, so when I have 3e to the negative x minus 2, this is going to be a shift down 2. This will change where the asymptote is. And we're just going to move everything down 2, so including the asymptote. And that's going to go through 0, 1. We don't have a whole lot of detail here, but we're just capturing the feel of this by hand, and we'll get the detail here when we do this graph with technology. Let's do a domain and range real fast. The domain of this blue graph is going to be all real numbers still. Exponents can be any kind of number, but the range is certainly limited. Looking at the blue graph, the lowest y-coordinate will be -2, but not getting there, right? It's going to be higher than -2 will be the possible y-coordinates. Y must be more than -2. Let's do this one with the technology, e to the x. So here's the original, and first let's do e to the negative x, and there's that reflection across the y-axis. Now what happens when I triple that? You can see the purple graph is triple the green graph. So, if you take any vertical line and you find the y-coordinates of the purple and green, the purple y-coordinate will always be 3 times as large as the green y-coordinate. And this is true no matter what x-coordinate you pick. So the purple will be 3 times as much. But the purple graph is still following the x-axis. When I put the -2, that's going to move the purple down 2, and we're going to have a new horizontal asymptote at y equals -2. So the purple graph is going through 0, 1, and it's going to approach y equals -2. Okay, the next exercise is, can we recreate the rule of a function if I just know its image? Notice that we are looking for a exponential function of this general form, a times b to the x plus c. Notice that there's no horizontal shifting allowed here. There's no plus or minus a number. First of all, we're going to figure out what base is correct, but we can only do a vertical stretch and a vertical shift. And when you limit yourself to vertical stretches and vertical shifts, then the location of the asymptote and intercept are going to be very significant. Look at the last example, right? This one here did not have a horizontal shift. Notice that the red graph has a horizontal asymptote right there, and this gap right here is 1 unit between the asymptote and the intercept. The orange graph was the same. It wasn't until we did a vertical stretch that we got a gap between the asymptote and the intercept. The asymptote for the green was still the x-axis, but its y-intercept was 3 units away from the asymptote, and that was revealed by the vertical stretch. So that vertical stretch can account for getting the y-intercept further away from the asymptote. Probably the easiest thing to track is going to be where the new asymptote is. That's going to be a result of the vertical shift. So if you shift down 2, that's going to move the asymptote with it. So the very easiest thing to find here is going to be the horizontal asymptote. It's pretty clear that y equals -3 is the horizontal asymptote. That tells me that we had a shift down 3. So I know the c will be a -3. And the next thing I want to determine is how far away from the asymptote is the intercept. What is this gap right here? And that's 2 units. That's going to be our vertical stretch. A is going to be a 2 in this case to get the vertical stretch that we want. So here's our function so far. The only thing left to determine is what the actual base is. Now looking at this image, this is a graph where the function is decreasing. That tells me that the base is going to have to be between 0 and 1. Let's see if we can confirm that. And to find the base, you just got to find any other point on this that's an obvious point. And the point that I'm looking at that appears to be an obvious point is right here. And we don't want that obvious point to be the y-intercept. That's not going to be helpful information, because when you plug in 0 for x, this will just get rid of the b anyway, so it won't help us find b. So all we have to do now is plug in 3 for y, at the same time you plug in -1 for x, and then this creates an equation for which we can solve for b. So that gives me 3 equals 2b to the -1 minus 3. I'm going to add 3 to the other side. We get 6 equals 2b to the -1. Divide both sides by 2, so we get 3 equals b to the -1. Remember, b to the -1 is really the same thing as just 1 over b, and so I can invert both sides and I get 1/3, therefore is b. And sure enough, we got a b that was between 0 and 1 as expected to produce this decay graph. The equation of this will be y equals, stretch factor was 2, the base is 1/3 raised to the x, and then minus the 3. And this is an acceptable answer. Now, one thing that could be done to rewrite this in a slightly different way is to think of 1/3 as 3 to the -1. And then when you have a base 3 right here raised to a power, and then you raise all that to another power, you multiply the 2 powers together. Right? You might recall doing something like x squared, and then you cube that, you get x to the 6th. So another way to write your answer is 2 times 3 to the -x minus 3. Now notice my use of the dot here. Do you want to put that there? Because if you don't, it looks like it's 23 raised to the -x. Another good way to make this clear that we are doing 2 times 3 to the -x is just to put the 3 to the -x in its own set of parentheses. That's pretty clear. But make sure you don't accidentally think of this as 23 to the negative x, and don't multiply this and say 6 to the negative x. That would be bad as well. If I have 2 times 3 squared, the order of operations would be to do the power first, so you have 2 times 9, you get 18. It would be a mistake to do 2 times 3 first and say 6 squared and get 36, right? These are not the same. But any of these here would be acceptable final answers. I suppose this was the answer that we were going for here because we specified that the exponent should simply be x, not negative x, for example. The next slide is compare the following basic functions by completing the tables and looking for patterns. All right, so we have an exponential function, 2 raised to the x, and I don't like to have 3 different functions on the same page all labeled the same way. Maybe it's better to call this one g and this one h. And so looking at the function f, the exponential function, when x was negative 3, we got 1/8 as the y. When x was negative 2, we got 1/4. When x was negative 1, we got 1/2. And then we got 1, then 2, then 4, then 8. When x increases by 1, right, if I just repeat this, and what's happening to the y's, we are doubling. Let's look at a power function. With an exponential function, it's the base that's constant and the exponent that's variable. And in a power function, the base is variable and the exponent is a fixed number. So a power function like x squared, when you square negative 3, you get positive 9. Square 2, you get 4. Square negative 1, you get 1. Square 0 is 0. Square 1 is 1. Square 2 is 4. And square 3 is 9. And so here the x's are still increasing by 1. I do notice that, look at the differences. So to go from 9 to 4, we subtract 5. Then we subtracted 3. Then we subtracted 1. Then we added 1, and then we added 3, and then added 5. So there may be something here we could do. How do you go from negative 5 to negative 3? We add 2. To go from negative 3 to negative 1, we add 2. Oh, this is interesting. To go from negative 1 to 1, we add 2. To go to 1 to 3, we add 2. And we go to 3 to 5, we add 2. The differences change at a constant rate. But that's going a little bit deeper than we need to go. Going from y to y, there is no pattern of multiplication or division that gets repeated. Let's look at a linear function, h equals 2x. All right, when x was negative 3, double that, we get negative 6. Double negative 2, we get negative 4. Double negative 1 is negative 2. Double 0 is 0. Double 1 is 2. Double 2 is 4. And double 3 is 6. Now, in this case here, again, we have the x-coordinates are increasing one at a time. And notice what's happening to the y-coordinates in this case. To go from negative 6 to negative 4, we added 2. To go from negative 4 to negative 2, we added 2. And we added 2, etc. This is indicative of a linear function. When your x's change by the same amount, and then you see your y's are changing by adding or subtracting by the same amount, then we have a linear function. Over here, though, in an exponential function, when the x's change by the same amount and you see the y's are changing by multiplication by the same amount, that's an indication of an exponential function. And then when you don't see either pattern, like the middle case here, we would be able to conclude from this data that the function represented here is not linear and it's not exponential, because I don't see a pattern of multiplication or division in the y-coordinates when the x-coordinates increase by 1. Patterns of multiplication, exponential. Patterns of addition will be linear. Suppose the value of a car in thousands of dollars is given by the function below, where t is measured in years. Use technology to do the accompanying tasks. So this is a graph of v of t. Now keep in mind that the output of this is measured in thousands of dollars. So if you were to say, hey, what's v of 0, and you plug 0 in, 0.85 to the 0 is 1, and then times 28 is 28. But this stands for $28,000 is the value of the car at time 0, so when you purchase it. Or you can say time 0 is now, so maybe today it's worth $28,000. But we can also say time 0 is when we purchased it, so we'll say this has a purchase price of $28,000. As t moves on, you can see how the value drops just from the image. And we're going to use technology to find the value of the car in 8 years. The calculation we would do here is simply say, okay, we'll plug 8 into this v function, v for value. And so we get 28 times 0.85 raised to the 8. So this is like multiplying 28 by 0.85, and you do that 8 times. It's like doing 85% of 28, and get a result, and we do 85% of that, and we do 85% of that, etc. So every year it looks like it's losing 15% in value. It's retaining 85% of its value the year before. That's the indication that we are looking at an exponential function, because as we go from year to year, we continue to multiply by 0.85, and that pattern of multiplication is indicative of an exponential function. Here's the graph of v of t. I'm going to change my scale just so we can see things. And if you want to know a v of 8, then you could just say, hey, what's v of 8? So this is one way to have Desmos do that for you. Another is to put a vertical line in here at x equals 8 and just see where it intersects the graph. Either way is a good way to get this y-coordinate. So at the 8-year mark, the value of the car is now at 7.63. Remember, that's in thousands of dollars. we know that that corresponds to a value of $7,630. Next question, when will the value of the car be $1,500? So that means I want an output of 1.5. Throw a horizontal line in here instead. Y equals 1.5. And then seeing where it intersects the graph. We can zoom in right there at that point of intersection. It looks like at 18.009, if we round to the nearest hundredth, 18.01 years is for the value to drop to 1.5, which corresponds to 1.5 thousand, which is 1,500. So on this graph here, right around here was that point. It was approximately 18.01, comma 1.5. And the other one was when t was 8. And these are the 2 points on our graph that help us answer the question that we have. Find when the value of the car will be $1,500. Let's say around 18.01 years from time 0, which we said was the time you purchased the car. Okay, and that wraps up everything that I wanted to discuss